All Academy. Always with you.
Hello my dear students, welcome to this online video session on basic thermodynamics. So in the previous session we have discussed a very important topic, that is application of first law of thermodynamics for the closed system. Now in today's session we're going to discuss the further topic, that is application of first law of thermodynamics for the open system. Then we're going to discuss the mass and energy balance in a steady flow process. And at the last, we're going to discuss the very important topic in today's session, that is the steady flow energy equation. So we're going to derive the equation for the steady flow energy equation. So without wasting much time, let us begin with today's session. Now, so as we have discussed the application of first law for the closed system. Now in today's session, we're going to start with the application, how it is the first law is applied to the open system. Now in engineering application, the most of systems are open system involving the flow of fluid through them. For example, the diffuser, heat exchanger, nozzle, rotary compressor, throttling valve, turbines. In these all, so you can see that, so from one side the some quantity of energy or the it will enters, the fluid will enters, and from another end the fluid will go out. Means there will be so change in the heat energy, change in the energy, change in the work. So all those things will be involved in this open system. Now how this first law is applied to these conditions, for example like diffuser, heat exchanger, nozzle, then rotary compressor, throttling valves, that we're going to discuss in details. Now the question is, how do we apply this first law of thermodynamics to such a system? That is very important part in this today's analysis. Means how we're going to study that one, whether is there any the assumptions has to be made, or is there any possibilities are there, or is there any things that we have to take care while applying the first law of thermodynamics to the open system. So basically when we are going to apply this first law of thermodynamics to the open system, so there are two possibilities while studying this one. The first one is the concentrate upon the certain quantity of fluid which is moving. Means, so in the entire flow of a fluid, I need to concentrate on the only a restricted quantity or only certain quantity of a fluid. This is a one possibility. And another one possibility is concentrate upon the certain fixed region space, which is called as a control volume. Means I have to analyze a fixed area, a fixed volume of the region on which my area of focus has to be given. So there are two possibilities. One is when to concentrate over the fixed quantity of a fluid. The second one is to concentrating on the fixed quantity of a space or the region, which is known as controlled volume. Now among these two possibilities, the second approach, that is concentrating on the fixed volume or the controlled volume, is a more convenient analysis and more commonly used. So among these one, which is the most commonly used, that is or easy to analyze, is one is controlled volume. The second possibility is a most convenient and effective analysis. Now what is this control volume? So we have got one word. We know that volume means the something that occupies some space. Now what is this controlled volume? So here you can see the small figure in this one. So I have mentioned a turbine and I have mentioned a dotted line. So this complete area comes under the control volume. Okay. Now if the attention is focused upon a certain fixed region or a space, is called as a control volume. Here which includes both inlet as well as outlet conditions. So in this turbine, I include both inlet conditions as well as outlet conditions. The whole system is controlled, and that is known as control volume. Our focus of attention is completely on the whole system. So such as things we call it as a control volume. Now consider the typical turbine. So as shown in this figure, the dotted line here, whatever you are seeing, the broken line represents the surface of a control volume, and therefore it is called as a control surface, means which differentiates this surrounding and the control volume. So this is a dotted line which creates the surface of a control volume, so it is called as a control surface. Now this is also called as a system boundary of an open system. It is also known as, this is also called as a system boundary in the open system. Now the method of analysis is to inspect the control volume surface and account for all the energy transfer to this surface. Means whatever analysis has to be made, I have to make on this control surfaces. Along with that, I have to take care that what all the energy transfer takes place through this surface. So that is a very important, that is application of first law here. Now further we should also carry out the mass balance along with the energy balance. You already know that whatever quantity of mass enter into the system, so that has to be taken outside, so that we have to balance it. Similarly, energy balance, whatever energy input is given, that quantity of energy has to be taken out by considering the some quantity of work. So that has to be taken care. So along with the other forms of energy interaction, so we must concentrate the two components, that is the mass balance as well as energy balance, while analyzing the control volume. Now since there is both mass transfer as well as energy transfer across the control boundary, why I have to balance this mass balance as well as the energy balance? Means whatever the quantity of gas entering into the turbine, so that will come out. So there is a transfer of mass. Okay, now whatever energy input is coming, some work is done, after some left out energy is taken out, so that has to be balanced. So this is about the how I need to analyze in the control volume. This is what the control volume is. Now what is this steady flow process? What is this steady flow process? The steady flow process, or the steady flow, means that the rate of flow of mass and the energy across the control volume are constant. Means whatever the rate of flow of mass and energy across the control surface is there, so that are constant. In most of engineering devices, there is a control rate of a flow of mass and energy through the control volume surface, and the control volume is the course of a time attains the steady state. Very important here, you know that steady state means the whatever the flow of mass and energy takes place through this control surface, and this control volume is in course of a time that attains the steady state. Now the steady state or condition of a system, any thermodynamic property will have a fixed value at a particular location and will not alter with respect to time. Means whatever the thermodynamic properties are we have identified in this controlled volume or in the controlled system, these properties will have a fixed value at that particular location and which will not alter with respect to time. Now let us go with a mass balance, then we'll go with the energy balance. Now what is this mass balance in the steady state flow process? Now the mass balance, here you can see the two different figures. Here you can check out that, so whatever the quantity of mass entering into this control volume, the same mass has to be coming out, it should come out. Similarly, here you can see this two entrance size given. One side it is coming with a mass m1, another at inlet it is coming with a mass m2. So only one outlet is provided, means so the both masses has to come out from this control volume. Now this is the balancing of this masses is a mass balance in the steady flow process. So the mass balance in the steady flow process is based on the principle of conservation of mass for a control volume. Here what is based on which principle this mass balance depends? It depends on the principle of conservation of mass for the control volume. So what it states, the net mass transfer to or from the control volume, please note that the net mass transfer. Here we are not discussing about the energy. Here we are only concentrating, or here we are balancing only the mass, entry of mass as well as exit of a mass. So the net mass transfer to or from the control volume during the time interval delta t. So delta t represents the time interval. During the time interval is equal to the net change in the total mass within the control volume during delta t. During delta t means during that interval, time interval means whatever the mass transfer, the total net mass transfer that is taking place in this particular time, so that will be same as that of it is coming out. So it says that whatever the mass inlet minus mass outlet will be our mass delta m. So that is delta m. So whatever mass inlet is coming in and mass outlet. So if I subtract from the mass inlet and mass outlet, the difference between, so it is a nothing but it is a difference between the inlet mass and the outlet mass. Now, so this conservation of mass relation can be simplified even further when the fluid is incompressible. So please note that this can be also applicable when the fluid is incompressible, which is usually in the case of liquids. Okay, now that can be used. We have used the equation, that is a continuity equation, that is A1 V1 is equals to A2 V2. A1 V1 is equals to A2 V2. So when this relation can be used, when the fluid is incompressible. Understood? Once again I will repeat the statement, that is the net mass transfer or to or from the control volume during the time interval delta t is equal to total mass within the control volume. So whatever total mass it is there inside this control volume, so that is the net mass transfer. Now this equation, I already said that this equation is, that is A1 V1 is equals to A2 V2. So that is a continuity equation. Now what is this A1? Area at inlet, and V is a volume at inlet. So this is A1 V1 is equals to A2 V2. Now coming to the energy balance, what is this energy balance? Already we have studied mass, entry of mass and the outlet of a mass. That study is known as mass balance in the steady flow process. Similarly, based on the principle of conservation of energy for open system, so we have to study the energy balance. So which can be expressed based on the principle of conservation of energy. The total energy crossing control volume as heat and work plus total energy of the mass entering the control volume minus total energy of a mass leaving the control volume will give us the net change in the energy of a control volume. It means that what if I want to identify the energy in the control volume, it is the nothing but sum of total energy crossing the control volume in the form of heat or in the work plus it is the net change in the mass. It is a net change in the mass crossing or entering or leaving the volume. So that is the energy balance in the steady flow process. Now mathematically this equation can be written as Q, that is the amount of heat added or heat rejected, minus work done plus energy inlet minus energy outlet is equals to delta energy, or it is the energy balance or the amount of energy within the controlled volume. What is that energy within the controlled volume? It is the heat addition or heat rejection minus work done by the system or on the system plus energy inlet minus energy outlet. That will give us the quantity or amount of energy within the control volume. So in previous case, how we have identified the mass within the control volume? It is the mass inlet minus mass outlet that gives us the mass within the control volume. Here in case of energy, the energy within the control volume, it is the the total energy crossing the control volume plus the total energy of a mass entering the control volume minus total energy of a mass leaving control volume will give us the net energy within the control volume. Mathematically, that can be expressed in the form of Q minus W plus energy in minus energy out will give us the total energy within the control volume. Now, the total energy is a simple compressible system. In a simple compressible system can be accounted in the three parts, means in a simple compressible system. So it can be accounted in a three different parts, that is, one is potential energy, kinetic energy as well as internal energy. What is the potential energy? It is a PE, kinetic energy KE, and internal energy we represent as U or sometime IE. So these notations we are using in a further derivation. So I have just told it is a potential energy, kinetic energy and internal energy. This energy is there in the simple compressible system. Now the very important uh, concept in today's session is, that is, steady flow energy equation. In most of time the examination, this derivation is asked for 8 to 10 marks. Sometimes they have asked for 6 marks. Derive the steady flow energy equation for the control volume, or derive the steady flow energy equation based on the first law of thermodynamics. In this manner they have, the question is framed in the examination. Now let us consider a control volume as shown in this figure. Now before going to derive this steady flow energy equation, so we must assume the following points. So the assumption has to be made for the while deriving this steady flow energy equation. Now this is a simple schematic figure that will gives us, or that will helps us to while deriving the steady flow energy equation. Now, what are the assumption? The first one is the mass flow rate remains constant, means the mass flow rate throughout the process remains constant. Second one, there is no chemical reaction in the system. Third one, only kinetic energy, potential energy and internal energy are considered in this analysis, because previously I have said for a simple compressible system, the energy accounted in the form of kinetic energy, potential energy and internal energy. So only these three parameters are considered for the analysis. Now only work and heat should interact between system and surrounding. These are the four important assumptions that has to be made while deriving or while studying this steady flow energy equation. Now here you can see this one figure. So this is a control volume and inlet which is at the datum head Z1 and outlet it is at the head Z2, and Q is the amount of heat entering into the system and W is the amount of work by the system. Now A1 and A2 are the cross sectional areas at inlet and as well as outlet. M1 and M2 are the mass flow rate of a fluid at inlet and outlet. Now P1 and P2 are the absolute pressure at condition 1 and condition 2. V1 and V2 are the specific volumes at condition 1 and condition 2. Similarly, the specific internal energy at 1 and 2. Then velocity of a fluid at condition 1 and 2. And Z1 and Z2 are the elevation, or you can say that datum head, or you can say head elevation from the datum line, that is Z1 and Z2. dQ is the heat transfer to the control volume and dW is the amount of work transfer from the control, work transfer to the control surface. Now, as per the law of conservation of energy, the total energy into the control volume will be equals to the total energy flowing out from the control volume. Therefore, that is mass energy into, why I have taken M? Because the M mass of fluid is flowing. So I have to consider the quantity or the mass of that particular fluid. So M into energy in plus mass into flow work plus amount of heat added, that is dQ, will be equals to mass flowing out plus mass flow work plus dW. Now this is a balancing based on the energy equation. So RHS is equals to LHS, means whatever the fluid energy work is doing at the inlet section, that has to be same in the outlet section. That has to be balanced now based on the law of conservation of energy. Now the energy flowing into that will be considered as a kinetic energy, potential energy and internal energy. So I have taken one here. It shows that at inlet condition. So M into Ke plus Pe plus IE plus mass into flow work plus dq, that will be equals to same as energy flowing out, means same again it has a kinetic energy, potential energy as well as internal energy at condition 2 plus the flow work at condition 2 plus dw. Okay, that is a work transfer from the control volume. Now this potential kinetic energy is given in the form of, so that is m into u1 plus g into z1 plus v1 square. So this is the sum of potential energy, kinetic energy and internal energy. So u1 plus g into z1 plus v1 square. Flow work is given by m into pv. P is a pressure and volume at condition 1, and here u1 is an internal energy, g is a gravitational constant, z is a datum head and v1 is the velocity. Okay, v1 is a velocity at condition 1. Similarly at condition 2, m into u2 plus gz2 plus v2 square divided by 2 plus the flow work is given by p2 into v2 m and amount of work transfer to the control volume. Now just rearranging, so if I take out m outside, I will take here m outside. So then the remaining terms will be u1 plus gz1 plus v1 square plus p1 v1 plus dq will be equals to, again here I will take m outside common, so that is m into u2 plus gz2 plus v2 square plus p2 v2 plus dw. Now rearranging the terms, we already know that. So what is that one? Internal, the product of pressure and volume plus the internal energy is nothing but the enthalpy, that is H. So we have already studied that one relation. So I will just replace U plus P1 V1, I will consider as an enthalpy. So M is equals to H1 plus GZ1 plus V1 square 2 plus dq. Similarly at condition 2, u2 plus p2 v2, it is nothing but enthalpy, sum of work done plus internal energy, that is I will consider it as an h2 plus gz2 plus v2 square divided by 2 plus dw. Now so this equation, so if I dq, if I considered by per unit mass, so then the equation becomes h1 plus gz1 plus v1 square plus q will be equals to h2 plus gz2 plus v2 square plus w. So this equation is known as the steady flow energy equation. This equation, and this question is repeatedly asked in the examination for 6 to 10 marks many times. So hope dear students, so whatever the concepts we have discussed in today's session, it is clear to you people. Still if you are finding any difficulties, you can comment it in the comment box and we'll try to clarify your doubts. And you can download the notes of this particular chapters and all the modules from the description. The link is given in the description box, and even you can follow us on our LinkedIn, and even you can follow us on the Facebook. So many things will be uploaded on those platforms also.
Click on subscribe button and press the bell icon to get updates from All Academy.